Welcome back to the workshop. We want to continue taking a look at the third section of the appendix, which is on proof methods. So we started taking a look at proofs by contraposition or using the contrapositive to write a direct proof. And we'd like to continue taking a look at that same example. So the proof or the theorem that we would like to prove is that if 3m plus n is even, then m and n are of the same parity. So using this one piece of information to find something about two things is a little bit difficult. Whereas if we take the two things and try to come up with one statement or one observation, that's a little bit easier to do. So we want to consider the contrapositive of it. So the contrapositive in this case is that if m and n are not the same parity, then 3m plus n is not even. That is, now what we're trying to say there is that 3m plus n is odd. I suppose we're not trying to say it's odd, we're trying to say it's not even, and that happens to mean that it is odd. So what we want to do is we want to do a proof by contraposition. So we're going to prove the contrapositive, which allows us to conclude that the original implication is true. So what I'm trying to say there is we need to prove this new implication. We still need to let m and n be integers. And then we want to assume that m and n are not the same parity. That is, one of them is even while the other is odd. So we've got two cases, right? Odd and even, and then swap. So case one, let's have m odd. So m is odd and n is even. When we have that, then m can be written as 2k plus 1, since it's odd, for some integer k. And n can be written as 2l, since it's even, for some integer l. Hence, 3m plus n is now easy to represent, and we can write it as 3 times 2k plus 1 plus 2l. A couple manipulations here. All right, this gives us 6k. 3 times 2 is 6. 3 times 1 is 3. 2l. Now here what I'm going to do is I'm going to pull out a common factor of 2 from a bunch of things, right? But this is not a 2 itself. We can think of 3 as 2 plus 1. So we have a common factor of 2 through all of these. So this is 2 times 3k plus 2 times l plus 2 times 2, or 2 times 1 rather. So 2 is 2 times 1. Then I still have a plus 1 there. So 3m plus n is written as 2 times something plus 1, which means it's odd, and in particular, it's not even. So hence 3m plus n is odd. Of course, let's observe that this is an integer first. So since 3k plus l plus 1 is an integer, 3m plus n is odd, since it's written as 2 times an integer plus 1. All right, so we began with our premise, assuming our premise, and we found our conclusion is true for this case. And now we want to take a look at the second case, right? Swapping even and odd. So we have case 2, and in case 2, we have that m is even and n is odd. And those are the only possible scenarios. N is odd, n is even, and case 2 here, n is even and n is odd. Okay, they can't be the same because then they'd be the same parity. So this is the only way for them to be different. All right, then in this case, n is equal to just a multiple of 2 for some integer k. And n is now odd, so that can be written as 2l plus 1 for some integer l. All right, hence, this allows us to say something about 3m plus n. All right, we want to show that it is odd, and when it's odd, it's not even. So hence, 3m plus n can be written as 3 times 2k plus 2l plus 1, because m is 2k and n is 2l, n is 2l plus 1. Pull out the common factor of 2 from these two terms to give us 2 times 3k plus l, and then I still have a plus 1 here. That gives me 2 times something plus 1, which represents an odd number. Since 3k plus l is an integer, that is a very important detail. It needs to be included. We can say that 3m plus n is odd. All right, so we began with the premise. The premise is true. Let's identify that really quickly right here. P is true, the premise. And then we looked at 2 cases, 2 cases, did some work for each of them, and then found that the conclusion found that Q is true in both cases. So now that Q is true in every case, we can write that the implication is true. So P is true and Q is always true. So when P and Q is true, the implication is true. Now in this case, what we've done is we've actually technically assumed not Q, and these are not P. Okay, so in the implication P implies Q, we assume the premise and we show the conclusion, and that's what we've done here. But for the original statement, if this then that, this is our P implies Q. What we've done here is consider the contrapositive, so not Q implies not P. So not Q is what we assume in this case, not P is what we're showing. Thus, let's see here, or therefore, we have if not Q, if M and N, if M and N are not the same parity, then 3m plus n is not even. Okay, so that's what we just showed. But that's not what we actually wanted to prove. We wanted to prove the contrapositive. Again, because the contrapositive of the contrapositive is the original statement. So thus, by the contrapositive, if 3m plus n is even, then m and n are of the same parity. R, there's only one R in R. M and n are of the same parity. And that is what we wanted to show, right? This is not Q implies not P, but by contraposition, by the contrapositive of this would in fact give us back that P implies Q. Okay, so again, the blue portion is the proof. That's all that I would expect to see. You don't need all these additional green comments when you write something up. That's just me trying to explain what we're doing here. All right, that's all that I wanted to show for this video. So I will see you guys back in the workshop very shortly.